Good morning, Michael.
morning,
It's
Matt.
to the hospital again.
Back to the hospital. We must be so sick.
Oh, I think we can do a fine job on this actually very challenging problem.
It is an interesting problem. What's nice about it is it sits in the same format as the regular L'Hopital's rule. Before we worried about the case, you look at this ratio, f of t over g of t. You want to know, does this go to a limit? And the answer is if f prime of t over g prime of t gets close to, say, some limit L, some value L, as t gets close to t naught.
So we did that in the case of 0, right?
Yeah, if this goes to 0 over 0, then, so I'm sort of writing this backwards. If this is true, then this gets close to L.
All right.
To the same L. Okay?
Yeah.
And the condition was, that's really bad writing, isn't it? Condition. Was something like this goes to 0, and the other guy goes to 0. So that's the one we learned before, regular L'Hopital's rule. We want to change just one thing, or two, depending on how you count. Change 0 to infinity.
Oh, well, I just got a funny feeling it's going to get interesting. And the reason is infinity is kind of a funny, quote, number, quote, and 0 is a well-known number. So this is not a well-known number.
It's not a well-known number. And so we have to be a little bit careful about what we mean as this goes to infinity. And you know, it was so important we did a separate video on it. But I'm going to summarize by saying, basically, give me any big number, like 53 million. I can eventually make this bigger than 53 million.
Right.
Give me another big million.
Doesn't matter.
Yeah.
You can always make it bigger.
Always make it bigger. So with that condition, we get this result.
Okay.
Now, what we want to do today is explain why this is true.
So let's do the geometry around this, because it's all geometry based.
So we can start with a nice xy plane. Here's x, here's y. And I'm going to put a curve in here, but the curve is a special curve where f and g are the parameters for the curve.
So now we parameterize not in terms of x and y, but if we look at our ratio, let's do f and g.
So I'll put g down here, because it's down there. And f will go up here.
So we're going from an xy parameterization to a gf parameterization.
Exactly. So let me now put a couple of points on here. I want to do this in a nice way. Maybe I'll do this point here. Okay, and let's put a curve. So here I've got a curve, a function of g and f. And f and g go out to infinity. So you imagine this thing going out to infinity. Okay?
Yep.
And these 2 points, I maybe can give them a name. Maybe this is like a T1 and T2. And out here is T0. So these guys are going, as T goes to T0, these things go to infinity and infinity. So you can think of it as way
So
out there,
T0 is a value here such that we're off to infinity for f and g.
That's right.
And in this way, we can parameterize the curve in such a way that we can deal with the ratio. And we've done this before in discussing the Cauchy mean value theorem.
Exactly.
So we could use the same idea.
We're going to use the same idea, the Cauchy mean value theorem. So let's draw a few lines. Remember with the Cauchy mean value theorem, we took 2 points and drew a line in between them.
The secant line.
The secant line. And what's the slope of this secant line?
Well, it's going to be the value of f here, g there, just the ordinary difference. F of t2 minus f of t1 divided by the difference with the g's. G of t2 minus g of t1. That's the secant line slope.
That's right. So we didn't actually write it on here because it was going to be a kind of a mess, but the x part is g of t2. Here's g of t1. So this is the change in the x, change in the horizontal part. Change in the vertical part, this is f of t2, f of t1. So the change is f of t2 minus f of t1.
So
That's
in
the
this
slope.
case, f of t and f of t2 and f of t1 are almost the same.
Almost the same. I have a little bit of a slope. But do you remember what the Cauchy mean value theorem told us about this? If I have two little curves, two little points on a secant.
There is a place somewhere in between t1 and t2. If we take the tangent, it's going to have the same slope as the secant line.
That's right. So here, this is roughly at this point.
And we call that c.
Okay. So this is at some point t equal to c. Should I call it t sub c maybe?
Yeah, t sub c is a good choice.
T sub c.
And then eventually,
So let me write it down. So what we did is we forced this line and this line to have the same slope. So this is the derivative, Tc, G prime, Tc.
and when we did that, the Tc was unique because we could take these points and kind of bring them closer together, right?
Well, we'll be a little bit careful. This thing could have been wiggling a lot, so there could have been several Tc. But all we know about Tc is that somewhere between T1 and T2.
Sure, I totally agree with that. If it's still true even if it wiggles a lot.
It's still true even if it wiggles a lot. Now, f of t, g of t. That's rise over run.
So we can draw a third line in this.
And maybe I'll draw it a different color since we're so lucky to have multiple colors here. I'm going to pick this point. And what's the slope of this curve?
Well, it's just going to be rise over run. So the rise is going to be f of t2, and the run is going to be g of t2, assuming that we start right here at the origin at 0. There we are.
Yep.
Oh,
So
we
that's
have,
this thing.
yeah, so we have three lines here to consider.
So I've got three lines. Two of the lines are parallel, so we've got this slope. This line doesn't look at all like this line. And yet somehow my theorem is telling me that whatever this thing is going to, then this has to go to. So how do I get these two lines to start looking
So we
the same?
could actually take a look at this and see my hands, and then as we slide up the curve and go to infinity, they're going to approach each other and basically overlay each other.
Exactly.
And that means that this limiting value ratio exists.
And that's, you've got the great intuition. You're a physicist, I think, aren't you?
Partly.
Partly. If you imagine these are like little rubber bands and you glue this one here and glue this one here, and you pull that out like with your hands, these two rubber bands, their slopes get closer and closer. And that's exactly what's happening. So long as these tangent lines are going to a limit, then this will go to a limit.
And so we have established that this limit exists in terms of the secant line. And then I assume what you're going to go to next is remind us about Cauchy and the application, now that we've shown that the secant slope and this linear slope here coincide at infinity.
Right. So this is exactly right. The Cauchy mean value theorem tells me if I take these 2 points, these secant points, these 2 points on the curve and draw a secant line, I can draw a tangent line that has the same slope. Now, the little tricky thing that we have to be a bit careful about is I fixed these points T1 and T2, but they have to also be going out to infinity. So later on in this limit, where as t gets close to t naught, so these are some T1 and T2 values, you might want to take some other values close here, for instance, and do this, and do this.
Oh,
And then we're saying these two slopes are the same, but this guy is the f prime over g prime, and that's very close to L now, because I'm going further and further out towards the f and g being infinity. And when I pull out this line now, of course, I'm going to draw it in blue.
if you draw the blue line, you'll see right away that that angle is going to be smaller.
Can I draw?
Yeah.
I think I can draw.
Bravo.
And you see they're very, very close.
Yeah, it's like 10 degrees or 5 degrees, and here it's like 45 degrees. So,
So look how close they are. And that is basically the proof.
and that's a fantastic result, very intuitively explained. Congratulations.
Thank you, Matt.